let's start. So I don't forget, there's going to be a lecture tomorrow. Okay, so we're going to have another short lecture tomorrow. Oh, and I don't forget to put the microphone up. All right. So let's do a very fast review of the Bayesian formalism. So we introduced the posterior distribution for the parameters theta given some data x. And using Bayes' rule, we wrote this as the likelihood times the prior divided by this normalization factor. And as I told you not to get confused with the different notations, pi, f, m, they're all, you can use p for probability and we're okay, but in the literature usually the likelihood is denoted as f, okay? This really, it's a Greek pi for the probability, and the normalization factor is m of x. All right. Yep.
What is the difference between that definition of likelihood and that one that you gave us, like I don't know, at the beginning of the class, like a product of?
Well, this what you're referring is basically how this likelihood is computed when you have a number of data points. So I take this whole thing and I write it as a function of theta as f of x given theta, or even better, a function of theta given x. So what you're referring to is the calculation of the likelihood. So I'm putting all of this together on this term, okay? So the normalization factor, this is very important for follow-up lectures basically in the course, is the integral of the numerator in the parameter space, right? Makes sense. You want to make this a probability. So this, when you integrate it, it needs to give you m of x. So m of x is equal to that. We introduce point estimates in the Bayesian way. And so I'm going to put all of them up. The most important is the map estimate, which is basically maximizing the posterior. Okay, and you see it here. It's sort of regularized maximum likelihood estimator, if you like. The posterior mean is another estimate, and quantiles, basically, if you're asking what's the posterior probability that theta is greater than some value, you just have to integrate the posterior distribution from a to infinity. And as I mentioned, you can appreciate these are integrals. This is an optimization problem. Eventually, you can solve this with Monte Carlo techniques. All right. We also discussed the predictive distribution. So if you have data x, and you're asking, what's the probability that x hat is going to be my next observation? We saw that the probability of x hat given x is basically an integral in the parameter space of the likelihood of x hat times the posterior and integrated in theta, okay? And if you compare this with the normalization factor in Bayes' rule, the difference you notice here is the posterior and here is the prior. This is the step that basically you need to do in your research if you want to say that you're doing Bayesian things. If you only use point estimates, you're not Bayesian. You cannot say I'm doing Bayesian statistics. You need to be able to average in the parameter space to say that you're working with in a Bayesian setting. All right, we did this example of the Gaussian. So we consider that we have a Gaussian, and in this case, we take sigma squared to be given. So the unknown parameter is really mu. So this is what we want to compute the posterior. So we're given a number of n samples, and we put some prior on mu, which is Gaussian, with some mean mu 0 and sigma 0 squared variance. So mu 0 is given, sigma 0 squared is given, and we want to find the posterior of mu. Okay? So what you were referring before, that's the calculation, right? That's the likelihood, all right, as a function of mu, okay? So if you take this likelihood, you multiply with the prior, which is also a Gaussian, you can, since you're looking for a distribution in mu, you can immediately recognize that there is mu squared and mu, so this is really quadratic in mu, so it's a Gaussian, all right? So if you close the square here, you can show that the posterior, it's a Gaussian. So let me rewrite it. This is the Gaussian, so this is the posterior mean, given by this expression, and this is the posterior variance. So you can see from the results that the posterior inverse variance, how do we call the inverse variance? The precision, the posterior precision, is the precision of the prior plus the precision of the model, where we add one precision of the model for each data point. Okay? And the posterior mean, basically, it's sort of a weighted average between the maximum likelihood estimate and the prior mean. So it's sort of not surprising, right? But this is what you get in between. And we considered two extreme cases. One case was when n goes to infinity. So when n goes to infinity, sigma n squared goes to 0, and mn, so if this goes to infinity, this becomes 1. So the posterior mean becomes the likelihood estimator. This goes to 0. So when you have lots of data, the likelihood defines everything. The prior has no role to play. Okay? And the other extreme, if you take that the prior is very spread, is like, you know nothing about the prior model, so you take the variance to go to infinity. Okay? So in this case, it comes out that the mean converges to the MLE estimate, but the variance is sigma squared over n. And if you think deeply, there is some similarities with the central limit theorem, but it's really two completely different stories, because the central limit theorem tells you that the sample mean follows a Gaussian with the actual mean and variance sigma squared over n. Here, there's no, this is the posterior mean, all right? So this converges to the MLE estimate. So we don't have basically a statement like, this is the sample mean to say the sample mean converges to that. It's the other way around, okay? But obviously there is some close, the equations look the same basically. So if you are to program this and you take, let's say, samples from a number of samples from this Gaussian, and you put this prior, okay, that you see here with this blue curve, as you start collecting one data point, the posterior will look like that, 2 data points like that, and then after 10 data points, the posterior sort of becomes narrower and narrower. So eventually, if you have a lot of data points, you are going to get the MLE estimate like a delta function. Okay? But you understand that the prior is needed. If you don't have a lot of data, effectively you're being pushed towards what the prior tells you, but the more the data, the less influence the prior has. You can, I am not going to elaborate, but you may ask a question that is very important when the data comes sequentially and you want to update your, the posterior mean and variance sequentially. You may ask, can I do these calculations as the data come? So if you collect one data point, can you update the posterior mean, the posterior variance? And the answer is yes. And here are the recursive equations. So if you want to find the posterior variance when you collect 10 data points, it's actually the posterior variance, the variance that you had when you collected n minus 1 point plus 1 over sigma squared. And actually, if you, I can tell you now, right, these Bayesian equations are recursive. So if I collect 1 point and I compute the posterior, then that posterior becomes the prior for the next calculation. And then again, that posterior becomes the prior for the next. That's why these equations look identical with the equations we had in the lecture last Tuesday, where we had only one data point. And this actually was the variance of the prior, and this was the mean of the prior. But now these quantities are updated with the mean and the variance of the posterior when we had collected up to n minus 1 data points. So the idea here is, right, that you can apply these calculations using all the data together and do the calculation, or you can do one data point at a time, you get the same answers. And you want to do one data point at a time. For example, if these data are very high dimensional, very expensive to keep in the computer, the best thing to do is use them for what you need, get rid of them. And these recursive formulas will allow you to do that. So again, this nature of the recursive calculations is given here. I have another derivation of this posterior mean and variance that I did before with closing the square, and I wanted, in preparation for what is going to come in a follow-up lecture, I wanted to tell you a more sophisticated way to do the derivation without having to close the square. I don't expect you to understand it, but I'm going to say it because we're going to see these formulas again and again and again later on. Okay? So you don't need to capture all the details. So let me concentrate first on some results that I am not going to prove today, but we will see them in a follow-up lecture. Okay? So imagine that you have a probability of x, all right, given by a Gaussian that has this mean and this precision. And then you have a conditional probability of y given x, where you notice the mean of y is a linear function of x. It's very important. So these systems are called conditionally linear Gaussian models, basically. Okay? So this condition of y given x has a mean that is a linear function of x. It's very important. Okay? And so the precision here is lambda, the precision here is L. You can actually use Bayes' rule. It's algebra. And one of the fundamental results that we will use all the time is that the probability of x given y, so we invert now the probabilities, okay, is given by another Gaussian by this, what otherwise looks a complicated formula, but a formula that we're going to use infinite times. So you have to believe me, if you use these two and Bayes' rule, this is what you get. And I want to make use of this for our problem. So what I have done is, I changed the notation a little bit to put it in some analogy with this. And I said, okay, let's consider we have a Gaussian. We know the precision of the Gaussian. And we want to compute the mean. And I name the mean x, just to put these equations sort of in a similar form. All right? So we want to compute the mean x. Will you agree with me now? Here is a prior in x. It looks like this equation. This is what we had before, right? That's a prior. And do you agree that this conditional is really this linear function of x? Right? Here I have x, and this general formula says ax plus b, where a is a constant matrix. So effectively, if I want to compute the posterior of x given y, I can use this equation where I put the correct quantities for mu, lambda, L, a, and b, and that's what I have done. And in one line, there is the formula basically for the posterior mean and the posterior variance. Okay? So you may want to look at this, because sort of tricks like this are essential to make life very easy. Otherwise, if you start doing this from scratch, it may take 2 or 3 pages of calculations, but in one page, basically we get the right answer. The answer here is identical with what we had before. The notation is different because I called the mean x and I called my data y. Okay, nothing else. This is similar to the example I showed you before, so I'm not going. Well, so you notice on this example, right, that maybe this example is good because it emphasizes if you have a prior that is very narrow, all right, you notice when you compute the posterior, okay, the posterior is pushed towards the prior. The prior is the blue curve. Now, if the prior here is, is very spread because you're not really certain about the value of the mean, so you notice that, you don't basically, it doesn't, especially if you have lots of data, you are influenced basically less by the prior, because the prior doesn't introduce any definite information. So in the case of a lot of data, obviously the posterior here will converge to the maximum likelihood estimate, and we have nothing to do with the prior. So the prior, I want you to think about it. It's extremely important when you have very few data. If you don't have enough data and you use the MLE estimate, the results will be wrong. Okay? So you need the prior to give you the right answers. I will not discuss the slide. You guys can read it. So we did inference on the mean of a Gaussian. So let's continue with Gaussians. Okay? Let's kill them to any extent possible today. So now the mean is known. And what I'm going to try to do is, I'm going to try using some data from a Gaussian to do inference on the variance. Okay? And actually the way that I have it on this and the follow-up slide, I will do inference on the precision because it's easier. Okay? So again, I collect a number of capital N data from this Gaussian. The mean is known. The precision is what I'm interested to infer. So what we do is, we're first going to write down the likelihood. And will you agree with me that the likelihood, when you take all this out of these Gaussians and you multiply them, the likelihood looks like that? Where is lambda to the power n over 2 comes from? You remember from the normalization of the Gaussian, right? Okay, so basically the normalization factor, you have lambda, actually you have, 1 over sigma squared a half, right? So you really have lambda to the power 1/2 times n to the power n, basically you get lambda to n over 2, and the product of this square exponentials comes a summation, and you get something like that. Okay. Now I want to introduce this concept at this point that is called conjugate prior, right? So we're going to introduce some prior for lambda to become Bayesian, and we want a prior that somehow, when we multiply it with the likelihood, will give us a posterior that will be the same type of distribution as the prior. So in essence, we would like to assume some prior, and then the posterior will be nothing else but an update of the parameters of that prior. And that's exactly what we call a conjugate prior, okay, in simple language. So looking at this, at the form of this likelihood, a nice likelihood, a nice prior, will be a gamma distribution for lambda, and you can see here why, all right? Here you have lambda of some power. A gamma distribution is lambda to alpha minus 1. Here you have some exponential in lambda with a minus sign. So in the gamma distribution, you have e to the minus beta lambda. This is exactly what the definition of the gamma distribution is, okay? And obviously the domain is from 0 to infinity, which is nice because the precision is positive. So what we're going to do is, we're going to assume some prior on gamma that on lambda that is a gamma distribution. We're going to multiply, and immediately you can see you're going to get lambda to n plus alpha minus 1, and then you're going to get lambda times b plus 1/2 of this term. So the posterior will look like this. The prior here, I put parameters a0 and b0. So this is the posterior, and immediately you can recognize, look at this, it's also a gamma, and an becomes n over 2 plus a0, and bn becomes b0 plus 1/2 of the sum of squares. And if you want to put the sample variance here, you get plus n over 2 times sigma MLE square. Right? No calculations involved because this is a visual effect, right? You look and you remember the definition of a gamma distribution is lambda to some coefficient minus 1. So obviously that coefficient is n over 2 plus alpha 0. N over 2 plus alpha 0. And similarly, b becomes b0 plus 1/2 of the sum squares. So it looks like that. This is too noisy. Okay. So this posterior for the precision lambda is a gamma distribution that looks like that. The nice of things in this particular example and a whole family of other priors that we will see as we go forward is that somehow you can put physical meaning to A0 and B0 just looking at this expression, right? So look at this, AN comes to be n over 2 plus A0. So if I ask you how many dummy data points the prior corresponds to. So here, these are my physical data, right? And the coefficient comes n over 2. So I'm asking you, if this comes from some prior measurements, dummy, that don't exist, but they are prior, how many of those? Extrapolating from this formula. This is n over 2, so this would be obviously 2A0 over 2. So 2A0 dummy prior measurements. Can you see that? This is sort of an interpretation. It doesn't mean anything. It will not help you in any calculation. But effectively, is the prior is like having 2A0 prior measurements, if you like. Okay? And similarly, you can, if you put this B0 to be, we said we're going to have 2A0 measurements, right? So if you put B0 to be equal to 2A0 divided by 2 times some variance square, you can see that the prior corresponds to some dummy prior variance that is B0 over A0. Only, you can do this only with certain distributions. And since you're already working in the homework set, the distributions that belong in the exponential family, basically you can put physical meaning on the parameters of the prior and interpret them as prior, if you like, effective measurements. Okay, so this is just a summary, cut and paste from statistics books of the, so you can have this things handy of this gamma distribution and the inverse gamma. I remind you, I had mentioned this in passing, if theta follows a gamma distribution, then 1 over theta follows an inverse gamma distribution, okay? So for example, if we use a gamma distribution for the precision, obviously for the variance, we're going to have to use an inverse gamma distribution, okay? The calculations don't always look as complex both ways, right? So in this particular case, working with precision, the algebra was immediate. There was no calculations to do, but with the variance is a little bit more complicated. So what I want to do is on this slide, I want to redo the same example, and instead of taking the precision as unknown, I am going to take the variance and I'm going to compute a posterior on the variance. Okay? I mean, you can say, well, if I have a posterior for the precision, I'm done, right? Because the variance is 1 over the precision, and you can use transformations of variables, and you can come up on this result. But I'm going to do it anyways, in a different way. So what I'm going to do is, I am going to use a prior for sigma square, that is an inverse gamma distribution that has these parameters that you see here. Okay? So the first coefficient is nu 0 over 2, and this is nu 0 sigma 0 squared over 2. So the distribution looks like that. Okay? And this is literally an inverse gamma distribution with these parameters, but when you plug in these parameters, in the literature they call this a scale inverse chi-square distribution, or chi-square distribution. Okay? So you can search on Wikipedia, they will give you directly this, but literally what it is, it's an inverse gamma distribution with some specific parameters. So if you take the likelihood we have, written in terms of sigma square, you multiply with this prior, immediately you can see that the answer, the posterior, is also an inverse gamma distribution or a scale inverse chi-square distribution. And the parameters basically nu are updated from nu 0 to nu 0 plus n. and the parameter sigma 0 squared is updated with sigma n squared, given by this nice formula. And it's easy to remember this formula because sigma n squared times nu is nu 0 times sigma 0 squared plus the sum of squares. Okay? So, bottom line, you use a gamma distribution for the precision as a prior. The posterior comes to be a gamma. If you use an inverse gamma, the posterior comes to be an inverse gamma. And these are the update formulas. Okay? What I wanted to show you, because I see it's written on that slide, if you really don't want to have to introduce any strong information from your prior, and you want to use what's called an uninformative prior, a prior that is as vague as possible, right? But still an inverse gamma prior. So what you do is you put nu 0 equal to 0. And when you substitute here, if you put this equal to 0, this uninformed prior, it's 1 over sigma squared. And I want you to remember this, because in many, many practical problems in machine learning where you have to put a prior on sigma squared, this is what you put, 1 over sigma squared. And literally what it is, it comes from the general formulas, but because you don't really want to put too much strong information, you use nu 0 equal to 0 here, and the result that you get is that this prior is 1 over sigma squared. Not 1 over sigma squared. Because later on we may see 1 over sigma coming on a complete different sort of situation. So here is on the posterior directly on sigma squared. So this is a prior. This is how it looks. So after you collect 2 data points, you get something like that. No, I'm sorry. This is already this is directly the posterior. So this is the posterior, the blue one with 2 data points, then 5 data points, then 50 data points, and 100 data points. So basically, you can see how you you can do this progressively as new data comes, and the posterior varies from very few data from here to something that is much sharper and around basically this value here. Okay. All right. Now let's do the homework problem. So we consider again the univariate Gaussian, and we said we're going to take. We took the mean to be the unknown, then we took the variance or the precision to be the unknown. So let's make life more interesting here. So we're going to take that both mu and lambda are unknowns. So we're going to have to do inference on simultaneously on mu and lambda. Okay, simultaneously. So we're going to, obviously, the likelihood is exactly what it was before. This is the formula, okay? The only thing I have done here, all right, and it takes some training to, not to derive this equation, this is obvious. So if you expand this square, you can rearrange this likelihood to look like this, okay? I remind you that this means it's proportional, so I don't indicate the normalization factor coming from the Gaussians, because we don't care. We only care about the terms that depend on mu and lambda. Every other term is not important. You remember the likelihood is a function of mu and lambda. Any other term that does not depend on mu and lambda, we don't care. Okay? So this is proportional to this. So I'm writing it in this form. Again, visually from where you are, you say, but how is that possible? Well, you know, this term here comes from this mu squared term there. When you expand, right? The other 2 terms come from xn squared and xn. So nothing really, it's just algebra. So now why this is of interest? Because we would like to have a prior that when we multiply with this likelihood, we will get a posterior that will be the same form as the prior. That's a conjugate prior. So we look at this form and we say, well, you know what? A prior on mu and lambda, that will satisfy that conjugate property has to be something like, okay, I see here lambda mu squared over 2 and lambda and a half. So maybe something to the power beta. Beta is a parameter. And then here I have lambda times mu times something, so some constant c, okay? And here I have lambda times something, so another constant d. Remember, in the prior, you're not going to put anything that involves data, right? So the idea here is we are looking on a prior on the joint distribution. It's a joint distribution of mu and lambda that somehow you can see if it's of this form, and you multiply the two things. Can you immediately see that somehow this beta will become n plus beta? Can you immediately see that this coefficient c will become c plus this summation? Can you immediately see that d will become, the update will be d plus 1/2 of the sum squares? So it's going to be nice conjugate prior, but somehow this looks weird. So the question is, what the hell of a distribution that is? It's very complicated, right? It doesn't look very familiar. It's some exponential there and something to the power. Maybe, we show terms that are exponential in the gamma and inverse gamma distribution, but there is a mu squared here that looks like a Gaussian, but then it's to a power. So what is that? So here's the idea. What you can do, you can take this expression and with some little algebra that certainly you should write in your homework, you can write it exactly on this form. And that form immediately reveals what type of distribution this is. All right? Notice what it is. This is a Gaussian in mu, right, for given lambda. Right? Because this is the square exponential of a Gaussian with given lambda. And what is the precision of this Gaussian? Beta times lambda. And what's the mean of this? C divided by beta. And what is this? This is a gamma distribution. Okay? So this is what it is. It's a normal gamma distribution. So basically the condition of mu given lambda is a normal times the probability, the prior of lambda, which is a gamma distribution. So effectively this is my prior. Okay? So my prior basically has it's a Gaussian on given lambda with this mean, this precision, and the gamma has these parameters that you see here. Okay? And I have you here the general formula of gamma, so immediately you can see the two things and how they relate. All right, if you multiply them, I'm going to bypass the slide and I'm going to tell you, no, actually I cannot bypass it because the answer is here, it's hidden. So if you multiply them, right, by design, the way we designed this prior, the posterior will be exactly of the same form. So the posterior of mu given lambda will have this mean, all right? Okay, and we have this precision, and then the gamma distribution will have this coefficient A, okay? What happened to Bn here? I have not indicated. Where's Bn? So I have not shown Bn since my slide ate it. So Bn must be where? Bn must be this whole parenthesis, I will assume, right? Is that the case? You guys worked on the homework. So when you get this right, so alpha n comes to be the prior alpha plus n over 2, okay? Prior alpha plus n over 2, and Bn is b plus this plus that, okay? And this, the Gaussian comes to have this mean and this precision, okay? No, actually I see here, right? So this is Bn, okay? So it's indicated here. I did not have space to put the whole Bn. So Bn is basically b plus all of these extra terms. And the trick in the algebra, right, is basically to close the square, to recognize that there is a Gaussian of mu given lambda, and once you identify that Gaussian, whatever other terms you have on lambda, you drop them on the second term, and the second term, and the second term then tends to be a gamma distribution. Okay? Now, you may say, will I ever do these calculations? You know, depends what type of problems you will do, because, these problems are tabulated already in the books, right? but maybe for your case, you have a lot of different priors, and maybe you don't need to do these calculations, but maybe you need to do some calculations that look like this. So if you haven't done this by hand once, your confidence that you'll be able to do something similar or something else, okay, is not going to be very high. But for us, we will be happy with these results, and you have to trust me that if you search even very popular statistics or machine learning books, trying to find all these results for Gaussians in one lecture, you will not be able to go anywhere, okay? So lots of people have some results here, the other ones give you 10 references. Here you have all the results together, which means there's a potential that somewhere there must be some mistakes on my slides. Okay? I think I prove everything when I type them, but who knows, right? So when you email me and you say you found a mistake, check it out first, okay? And then inform me so I don't panic for nothing. All right, so this normal gamma distribution looks like this, okay? All right, and somebody may say now, okay, we did this with the precision, can I do exactly the same concept with the variance? Absolutely. If you want to compute the posterior on mu and sigma squared, not mu and lambda, what you can do is you can use actually what is called a normal inverse chi-square distribution. Really what it is a normal distribution given sigma, okay, for mu, and then basically what you have is an inverse gamma distribution here. So rather than having normal gamma, you have normal inverse gamma, okay? And I give you all the results basically. So this is the posterior mean, all right? Nice results, very nice form, you will not be able to guess that the results look like that. And again, we see this new sigma square, new 0 sigma square coming up. And once you have this posterior, you know what? You can do a lot of fancy things. So for example, somebody may tell you, I don't really care about the mean, I'm only interested in the variance. Can you tell me what is the posterior of the variance? And then you know what you need to do is you need to use this formula and integrate mu out. That result will be completely different from the result if you take mu to be constant. Right? If you say I'm going to do inference only on sigma squared, that's one thing. Here what we do is we do inference on mu sigma squared, and this calculation is the marginal of that posterior. That result is very different. Because in essence, you notice here, is like you average over all possible posterior values of mu. So this is the correct calculation actually when you want to use a posterior on sigma square when you don't care about mu. Okay? And I give you what the mean of this is, and I mean, since this comes to be an inverse gamma distribution, you can look on the tables and write the mean, the mode, the variance, and sometimes, especially if you do experiments and you want to tabulate things, these are the type of values you need for these distributions. So what I have here is I have this normal inverse gamma distribution, this normal inverse chi-square distribution for the particular parameters, and I show you how the distribution looks like. So this is, the axis is the mean and the variance, and you notice this value k0, the higher it is, the more confidence you have on the mean in the normal distribution, and this coefficient is 0, the higher it is, the more confidence you have on the mean of the variance. And you see here, when k0 goes up, this becomes more narrowed around the mean value of 0, and here when this goes up, it becomes more narrowed around the variance basically of 1. Okay? So this is how these distributions look like. By the way, if you see any of these links not to be working, so you may want to literally download this toolbox in MATLAB It will only take a few minutes, it's straightforward, and then sort of run these little applications and maybe go and change the parameters to see how things look like and what these distributions literally mean, because they have too many parameters, so you need to get a sense of what exactly they mean. So let me ask you, okay, so before I gave you the results for the posterior marginal of sigma square. Now, if I take the posterior marginal of mu, it says here the distribution that comes out is student t. And I'm going to ask you, have I ever said anything about how student t comes? You remember when we introduced the student t distribution, we said something about it. What we did is we took Gaussians of different precisions, right? And we average over all possible precisions that follow a gamma distribution. You can think the same thing, right? You can take Gaussians with different variances, an average of over all possible variances that follow an inverse gamma distribution. Isn't it this what I have here? Right? You remember this is normal times an inverse gamma. So effectively, what you do is you integrate sigma square out, and obviously the distribution will be student t, exactly as we had seen before. So, so this, you know, if you write this, you know explicitly what the mean is and the variance and whatever you want else to do with the student t distribution. I mentioned before that if you want to be completely uninformative, the uninformative distribution is basically, even for the joint, is 1 over sigma squared. So the idea is for the uniform is constant, it's 1 in an unnormalized fashion, and for sigma squared, it's 1 over sigma squared. And these are the parameters that you need to plug in the general formulas to get actually this uninformative distribution. So if for these parameters you're going to compute the student t distribution, you can show actually that the posterior of marginal posterior of mu is a student t that has a variance that is s squared over n, where s is given by this, okay? And so a very common calculation that you will see in practice, people will ask you, can you give me the central interval for mu where 95% of the probability is? And you remember that interval is the mean plus minus 2 times the standard deviation, but the standard deviation here is s over square root of n, where s is this formula here. So lots of times, in lots of books, they will be doing this calculation, they never tell you from where it comes. And actually, a lot of times, the calculation possibly may not be even coming from Bayesian analysis, okay? But a Bayesian analysis basically gives you ideas on the posterior of mu and sigma squared, the marginal of mu, the marginal of sigma squared, and everything else. All right, so that was your homework. So let's now complicate things and discuss the multivariate Gaussian. These formulas actually are, they're not complicated, but you know, when you do them the first time, it gets painful, okay? And the results are extremely essential because remember, at the end of the day, everything is about Gaussians, okay? So I don't think in the context of this course we will see analytical formulas like this beyond what you will see now for Gaussians, okay? Good news is the procedure is identical with what we did for the univariate Gaussian. It's just that they're higher dimensional. That's it, okay? So let's take the case that we know the variance. So we're going to start with inference on the mean. The mean now is a vector, right? Can be 100 dimensional, 1,000 dimensional. So what we're going to do is we're going to put a prior on mu exactly as we did before with some known variance, a covariance metric sigma 0. So this is a Gaussian. So we multiply the likelihood times the prior, and we rearrange it. All right, this I only show you here the log. You know, I show you the exponential if you like, and you can see if you put the mu squared together, you get this. So this is really the inverse variance for the posterior, and this is the inverse variance times the mean. You remember when you have a Gaussian, right? You have x minus mu times sigma minus 1 times x minus mu on the exponent. All right? So what effectively we want to do is we want to discover that, and by closing the square we can see that the posterior of mu has a mean that looks like this expression here, and it has a covariance matrix. It's actually identical with 1D. You remember in 1D we said the precision of the posterior is the precision of the prior plus n times the precision of the of the model. Okay, so here instead of the precision we have matrices, right? The same identical formulas. There's nothing else. I mean, if this was something different, you will worry because you will say, how is it possible that this result doesn't give me the same answer as before if my dimensionality is 1? Well, it does. All right? And you notice the averages for the mean involve now matrices. Right? They involved matrices before they were scalars. No big deal. All right, so let's now do the problem where the mean is fixed and the precision is unknown. All right, so the mean is fixed, the precision is unknown. So I am writing the likelihood, the determinant of the precision to the power n over 2, exponential of minus 1/2 trace of s times lambda. Do you remember the trick that I told you need to learn? Remind me, what's the trick? With a trace. Huh?
Cyclicity? The cyclicity? Cyclicity?
Simplicity?
No. Cyclicity?
Somebody help me, another word, so I can understand.
Trace is a scalar,
So basically we said that exponent is a scalar, right? So we can write the trace, and trace of AB is equal to trace of BA. So basically, by rearranging it, we got the precision matrix. Actually, I can put the precision if I like it on the left as well. It makes no difference. But basically, we got this data center matrix around mu. So so we get the trace of S mu times lambda. Okay. And this comes from the normalization factor, because lambda, the precision is unknown, right? So we have to keep that. You notice here in the notation, this is very important, I put S mu, so this is the scattered data matrix as it's called, but it's scattered, we basically take the data around mu, so I denote this as mu. And this is important because later we're going to have other matrices that will be around not mu, but maybe the sample mean, okay? But when you do this calculation, the immediate result, basically, this is what it is. I mean, there's no algebra involved, right? This is it. Okay, so we're going to now, this is going to be new to you, right? So we're going to need to have a prior model for the precision, but the precision is a matrix. So we need to have a distribution over symmetric positive definite matrices. Because the precision is symmetric, it's positive definite matrix. So you say, wow, what is that? A distribution over matrices. Why not? Right? Why not? I mean, if the unknown is a matrix, we need a distribution over symmetric positive definite matrices. And the conjugate actually prior that we will use is what is called the wizard distribution, and I copied the formulas for you here. It involves the determinant to some power. These are mu are the degrees of freedom. D is the dimensionality, all right, the same as for this Gaussian, and then W is a matrix that comes, symmetric, positive, definite as well. So when you take samples from this distribution, those samples are of symmetric, positive, definite matrices. Now you may ask me, how do I take samples from this distribution of matrices? Another subset, all right? Another course. So looking at these equations and trusting this, taking this as a definition of the wizard distribution, can you see actually that if you multiply the two things that they are conjugate, that you will get a conjugate posterior? So the parameters here were W and nu. Can you think that somehow when you multiply them, you'll be able to come up with a wizard distribution that is the posterior, where instead of W and nu, you will have some updated matrix W and some updated coefficient nu. Can you see that? I mean, if I multiply this by that, right, immediately you can see my, this n will end up there. And I'm going to have n plus nu minus d minus 1, right? Similarly, here you have w minus 1 is going to be added to s. So effectively what do you get, all right? You get, where is my result? I don't have the result of the posterior. So the posterior basically comes to be a wizard distribution, and point me, where are the results? Okay, so I eliminate them because they are obvious, okay? Somebody ate them, okay? So effectively, immediately you can see that nu becomes nu plus n, and the new W posterior inverse will become W minus 1 plus Sm, okay? And that's the answer. And you can repeat the same problem where the unknown you don't take to be the precision, but you take it to be the covariance sigma. So basically, you write the likelihood in terms of, you keep sigma rather than lambda, and the conjugate prior is obviously the inverse wizard distribution. This is identical to the gamma and inverse gamma, right? So you can think of the wizard and inverse wizard distributions being extensions to multivariate variables of the gamma and inverse gamma distribution. That's what they are, okay? And so this is what you get, and the rest is history. So, okay? So here I give you explicitly the results for the posterior of sigma. It's an inverse wizard distribution with degrees of freedom n plus nu 0, and this matrix, the posterior scatter matrix, if you like, to being the posterior scatter matrix of the data plus this posterior, the prior S0. Now, an interesting calculation that you do often is actually when you are interested, let's say, to do inference on this metric sigma, right? So let's think of the following problem, and I'm going to give you actually results on this problem shortly. Suppose you collect some data, all right, and somebody tells you, from this Gaussian, go and estimate sigma, all right? So obviously, this calculation will give you the exact posterior of sigma, but if you're a machine learning person and you really want to do just a very fast answer, you will say, I'm only happy for the map estimate. Don't give me the whole thing, I just want to know what the map estimate of this posterior looks like. So the map estimate actually, if you look on the formulas I have for this inverse wizard, you can immediately write it down, okay? And so this is how the map estimate is going to look like, okay? And so what I'm going to do is, I'm going to show you a calculation that people, even who are not Bayesian, they do all the time when they want to compute the covariance. So what they say is, look, since I took the mean of this distribution to be known, let's take this to be the sample mean, right? That makes sense, okay? So you take mu to be the sample mean, and then this data matrix Sm would be basically around the sample mean. You remember that is the summation of xi minus the sample mean, then xi times minus the sample mean transpose, all right? So S mu becomes Sx bar, that's the sample mean. So the map estimate for sigma it turns out that it is a weighted sum of this posterior covariance matrix sigma 0 and of the MLE estimate. And the MLE estimate for the covariance, we already did this, on an earlier lecture, right, on Tuesday. Okay, so it comes out that the map estimate is a weighted average, right? This is from the prior mode. Actually, this exactly comes to be the prior mode. So the prior is an inverse wizard, has this mode, and this is the MLE estimate. And lambda is defined explicitly as n0 divided by n plus n0. And what is n0 is this quantity here, the degrees of freedom plus the dimensionality plus 1, all right? So the people who use this formula without any Bayesian understanding, they say this is a good answer, it works. Just be careful what you use for lambda. So they do, and I don't want to elaborate, right? They do cross-validation and, play around, and they say that lambda works. In our case, really, the lambda is defined explicitly from the Bayesian analysis, but I want to show you in practice how this problem will work, and some amazing result that you can get, that if my TAs were here, they can give you to you as a homework, all right? Of course, we have to solve it, which makes it another story, okay? So here is how you compute this map estimate. So sigma 0 is the prior mode, and somebody will say, wait a second, I have to select a 0, very complicated, what is that? I have to select n0, which involves this, degrees of freedom for this inverse wizard prior, so it's too complicated for me. So here is what you can do in practice. People use, instead of sigma 0, they use the diagonal, so a matrix that has only diagonal elements, extracted from the MLE estimate of sigma. You remember the MLE estimate? It's the empirical covariance, basically, all right? So they use sigma 0 to be the diagonal of the MLE estimate, and then the map estimate, you remember it was the weighted average of the prior mode and the MLE estimate? So in that case, the map estimate comes to be as follows. If I is equal to j, it coincides exactly with the MLE estimate. If you are off the diagonal, is 1 minus lambda times the MLE estimate. So basically, if you are off the diagonal, you regularize the map estimate and you put it towards 0 value, which is the prior values. So effectively, again, the only thing you do is, instead of using this and having to set S0 and N0, use sigma 0 to be the diagonal of the MLE estimate of the covariance. So I'm going to show you an example. Suppose I throw at you a 50-dimensional Gaussian. I don't tell you much, okay, all right? So I'm throwing at you 50-dimensional Gaussian. I tell you it's 50-dimensional, and I give you one data set that has 25 samples, then I give you 50 samples, and then 100 samples, and I ask you to estimate me the covariance matrix. So it's 50-dimensional, but even with 25 data points, I want you to estimate a 50 by 50 matrix. Can you do that? So again, the matrix is 50 by 50, and in this case, I'm only going to give you 25 samples. Of course, these are samples from a 50-dimensional Gaussian, right? So 50-dimensional vectors. So here's what you get. Let's start, in the case of very few data, 25. What you see plotted here is the eigenvalues of the covariance that you compute. Right? For plotting purposes, we need to show something, right? So showing the eigenvalues of this covariance is a reasonable thing to do. So this darker line that you see here is the true value. So using the true covariance from where the data came. The blue is the MLE estimate, and this number k that you see here is the condition number of the covariance matrix that you calculate. And for those who know linear algebra, the higher the condition number, the more what the matrix is. The more singular. So the matrix here is very singular. Actually, the eigenvalues are garbage. But look at the map estimate. The map estimate is this dotted red line, right? Still, even with 25 data points, looks good. And if you continue, of course, with more data, all right, basically you get almost the exact answer. So again, this just a point estimate. It allows you to estimate a 50 by 50 matrix by only having even 25 data points. So hopefully you get sort of an appreciation of what type of calculations is feasible here. If you try to do this with MLE without regularization, basically the results that you get are ill-posed. You cannot get the right metrics. With a little bit of regularization through this map estimate, effectively, even with limited data, you get the right answer. So this is a very nice example. And actually, to implement it literally, this takes 2 lines. And you can actually program it in 1 line. And what are those 2 lines? If you have the data, you compute these metrics, and then you say sigma map equal to this, equal to that, done. That's it. No other calculations. Okay? All right. So someone will say, wait a second, now you have to tell us even the more difficult case. How about if both mu and precision, or mu and the covariance are actually unknowns? So let's take the case where we have a number of samples from a multivariate Gaussian. So the mean is unknown, and the covariance lambda, the precision lambda is also unknown. What do we do? Exactly what we did in the univariate Gaussian. So basically, before, if you remember, we had a normal gamma, a normal inverse gamma distributions. So what we're going to have for lambda, we're going to have a normal distribution given lambda, all right? This will tell you basically the strength of this. And then for lambda, we're going to have a Wizard distribution. So this is a normal Wizard distribution, which is similar to a normal gamma distribution. Nothing really new, all right? So instead of having normal times a gamma, now we have a multivariate normal times a multivariate Wizard distribution, all right? So we're actually copying the results from the 1D case to the higher dimensions. And so if you, I give you all the results actually that you need to know. Some of the formulas contain substantive intermediate results that may be beneficial to you in later calculations. So, so here is the likelihood, right? I keep all the terms I keep actually all the terms here, all right? And you notice what I have done is, here I had this x minus mu transpose lambda x minus mu. I rewrote this, okay, because it's going to be needed. I wrote this on a quadratic term that involves mu minus the sample mean. And then what I get, instead of having a scatter matrix around mu, you know what I have here? A sample matrix around the sample mean. You remember I was telling you? So this matrix here is summation of xi minus x bar times xi minus x bar transpose. Okay? And the subscript means it looks like this without the lambda, right? But instead of having mu here, I have x bar. So this and this together, they actually give you this. That's why I put them in blue. And this is sort of an algebra that you may benefit if you prove it, takes 1 line, and if you use it. Because in a lot of calculations, it may be helpful to sort of use this trick. So here is the likelihood. Here is the normal Wizard distribution. I put the normal of mu given lambda. I put the Wizard distribution for lambda. I even give you the normalizing factor for the normal Wizard distribution. And you multiply them. And at the end of the day, you combine everything together. And the answer is, show me what the answer is. I mean, I see the answer, right? I want to see it explicitly. And here is the answer. The answer comes because this is a conjugate prior. It's also a normal Wieser distribution. So it's a Gaussian where the parameters mu and k have been updated to mu n and kn. Here is mu n, here is kn, and times a Wieser distribution where the matrix that we had before has been updated to Tn and the degrees of freedom to nu n, and Tn is given like this, and mu n is given like that. Okay? And again, I give you here actually explicitly what Sx bar is, right? So this, you know, this term here gives you the uncertainty in the mean, because this is the prior mean, this is the sample mean, they're not the same. So this is the uncertainty in the mean, this is the uncertainty in the data, it's the empirical basically covariance of the data, and this is the uncertainty that comes from your prior model. So when you add all this together, basically you get this nice formula, and the result is a normal Wieser distribution. And what you can do is, if you're only interested in lambda, you can integrate mu out. If you are only interested in mu, you can integrate lambda out. And if I integrate lambda out, what type of distribution will we get here? If we marginalize and we integrate lambda, what type of distribution do you expect to get from this? You remember again, if you have a normal for different precisions and you average with precisions coming from a gamma or a wizard here, you get what? Student t. All right, so you know what the answer is going to be. You don't have to redo it because it's in the books by definition. Okay? So the posterior looks like that, and what I want to, you know, because I'm going to be using some of these ideas when we discuss Bayesian model selection later on, right? So I am just telling you what the normalization factor of this multivariate Gaussian Wieser distribution looks like, right? So if I take all the terms that involve mu and all the terms that involve lambda, what is left is a 1 over a normalization factor that looks like this. And this normalization factor, how do you get? Looks very complicated. It involves nothing but the normalization factor from the Gaussian, all right? And I do not account in the Gaussian the terms that involve the determinant because all of them are here, all right? And then this is the normalization factor from the Wieser distribution. So what I want you not to remember a formula or anything like that, I want you to remember that the normalization factor for this Gaussian Wieser distribution is known and it's in the notes. Because that normalization factor has physical meaning that will allow us to do model selection later on in the course. In a much more interesting problems than playing with the Gaussian, but remember that zeta n looks like that. And this is the normalization factor similarly for the prior. So these are the prior quantities, K0, T0, etc. And these are the posterior Kn, nu n, and Tn. Okay. So I give you all the intermediate results, right? I said if you want the marginals, the marginal of lambda is a Wieser distribution, the marginal of mu is a student t distribution, you know, okay? And if somehow you're only interested for point estimates and you don't want to have to deal with complex distributions, here are the map estimates. So if you really want just to know the values of mu and lambda, you can plug them in. Basically, this is the map estimate for the mean. This is the map estimate for the precision. And you know, if you take specific choices for the prior, you can basically recover back the MLE estimate as well. All right. Let me see if I will give you this. Well, so let me we have 5 minutes, okay? And rather, so this results here, they give you, in addition to the marginals, I have the calculations for the posterior predictive distribution. You remember the posterior predictive is if you have some data and you compute the posterior parameters of for mu and lambda, you want to know what's the distribution of the follow-up observations in the future. And to do that, you need to integrate both in mu and lambda. So it's the likelihood times an integration of the posterior in mu and lambda. So if you do that, actually, the calculation comes to be a student t-distribution. And this is very important formula, because it allows you to predict what the next measurement will look like. Okay? And so in this formula, effectively, is the likelihood times the the posterior and an integral over mu and an integral over lambda. Okay? And I simplify, if you use an uninformed prior, I give you actually formulas for the predictive distribution. And usually in statistics books, you may see these formulas, you will never see from where they come. Okay? So they come from the general results, and then if you take some coefficients to be certain values, so you get an uninformed prior, then you get usually what is listed in the books, and you can use those if you want to tabulate your uncertainty in future predictions. You can use basically those estimates that you see there. So I have 3 minutes. I want to show you a calculation that we are going to do later in the course, but I want you to see it now, all right? You remember when, so this is the posterior distribution of mu and lambda, and it's written as the likelihood times the prior divided by P of D, and P of D is the probability of the data, and it's called model evidence. So when you have a lot of models, right, and you say what model best explains my data, the only thing that you have going is that quantity P of D. And you say, if I have a lot of models, the best model that explains my data is the one that maximizes the probability of the data. I mean, if you have some observations, you want the model that best explains what you have observed. So you want to be able to compute this P of D. So what I give you here is, using the normalization factors of this normal wizard distribution, I give you a trivial calculation of P of D. Remember, the way we derive this posterior, we computed the likelihood that involves all the terms in mu and lambda, but we didn't bother about the coefficients for normalization on the front. And we did the same thing for this and the same thing for that. So really, if you look at both sides of this equation, the terms that involve mu and lambda cancel on the left side and cancel on the right side. And really what you're left is with the normalization factor of this joint posterior, the normalization factor that you get in the likelihood, and the normalization factor that you get in the prior, and that allows you to compute P of D as 1 over the normalization factor of the prior. This 1 over, on the denominator, you're going to have 1 over Zn, which is the normalization factor of this posterior. And then you have a normalization factor coming from this Gaussian, which is 2 pi to the power n d over 2. And then this evidence, the probability of the data, is given by this complicated formula. And that formula is the formula that you have to maximize if you want to find what model best explains the data. And that's really a very sort of Bayesian way to look at interesting things, okay? Again, we will discuss this in details later in the course, but I think it's nice to have this formula available for you, ready to go. I am not going to do this inference on mu and sigma. It's basically identical to what we have done before with the normal and inverse gamma distribution. So effectively, when you are doing inference on mu and sigma, not mu and lambda, instead of using wizard, you use an inverse wizard distribution. So I'm repeating the same calculations basically once more, all right? They look a little bit different, not very much different, and I give you all the results, you know, how the posterior looks like, you know, how the map estimates look like, how the marginals look like, and even how the results relate with the 1D case. And I even give you the model evidence computed once more, this calculation for this problem. You may want to look on this derivation and ask questions now, because if you understand it sort of now for this problem, it would be sort of a trivial task to actually use it in later in the course and in your research as well. All right, so what we're going to do is 146. On Friday, we're going to go and discuss the limit left details, very simple subject on the exponential family that we need for the homework, and that will complete everything you need to know about the homework. Okay, so I will see you tomorrow.